So in the last class, we continued the discussion on algebraic expansion versus combinatorial expansion or edge expansion, and we showed these two theorems. Theorem 1 saying that algebraic expansion means edge expansion, and theorem 2 talking about the converse. There were some mistakes in the constant, so that I have corrected. You can look at these new slides. I corrected here. Then this proof was fine. So now to prove theorem 2, last time we started this proof, we actually ended this proof. So there were two claims. Claim 2, I have corrected the constant again, and in this proof there was some mistake which is now corrected. So we look at this expression 1 minus lambda 2 greater than equal to numerator divided by the denominator. Numerator estimate is at least 4z square and denominator estimate is this thing 8 times v to the 4. Okay, so the ratio comes out to be z square divided by 2 times v to the 4. So you get this constant square root 2. Okay, so this part I have corrected, and then we started an interesting application of explicit expanders, which is that suppose in a general randomized polynomial time algorithm you were using, or the algorithm was using r random bits to get error probability smaller than 1/3. So how can you make the error probability exponentially small, which is 2 raised to minus k? So the obvious boosting will require repeating the experiment k times, which will give you r times k random bits. Instead of that, we can do it in r plus k random bits. Okay, the same error probability, exponentially small. So the way this is done is, we will start with a very large expander graph, which will be very explicit. Okay, so for any vertex, the vertex label is r bits, which you can think of as the random string supplied to your randomized algorithm. But there are d neighbors only. Okay, think of d as 3. So there are d neighbors, which means that you can do a random walk easily on this once you know the neighbors. Okay, that's the explicitness condition, and the spectral gap you assume is larger than 0.1. So based on this, you do a random walk starting from v0 for k steps, and that will give you k vertices in the path. So you have k kind of pseudo random strings. This you can use in the randomized algorithm, or you basically are repeating the algorithm k plus 1 times. You repeat the algorithm k times because now you have k pseudo random strings, and then take the majority vote. Okay, that was the idea. How many random bits did you use in the random walk? So for the first one r, and for the remaining one it's only k times log d. So log d is a constant, absolute constant. So this is just like r plus k, much smaller than r times k. So what is now the error probability? That is the main thing to calculate. So let us do that now. So we will be proving Aitai-Komlosh-Zemerides theorem, which will basically look at the probability of the random walk being stuck in the bad vertices. Okay, bad vertices, think of them as those strings labeling vertices that are bad for the algorithm. The algorithm makes mistakes on those choices. Let us first show that the probability of the random walk being always in this bad subset B is quite small. So if you are doing this k step random walk, then it is beta plus lambda to the k. Beta is the fraction of bad vertices, okay, out of the total number of vertices n, beta n are bad, and lambda is the second largest eigenvalue. So if beta plus lambda is smaller than 1, this is an exponential drop in k. So let's prove this theorem in blue, and once we have a proof of this theorem, then we will show how to get at least half of the vertices outside the bad set B. Okay, so that calculation will be similar to this. And then you can use it in the algorithm. So let's start the proof of this. Let A be the normalized adjacency matrix of the graph G. But now, since you only want to consider the case where every vertex is in B in the random walk, you will actually only need a part of the adjacency matrix, the part which is B cross B. Okay, so we will express the probability as a matrix product. Using the submatrix A B cross B, because you don't even care in this random walk about the vertices outside B. You only care about vertices in B and then walking to B. And then analyze using the spectral norm. Spectral norm of A and the size of B. This is also important. If B is everything, or in the other case, if B is empty, right, then the probability will be 0 of always being in B. But if B is large, then the probability will be high. So probability will really depend on the size of B. So this matrix product, submatrix, and spectral norm. Okay, these are the keywords in this proof. So let us do this formally. So let P be the identity submatrix. Let it be the n cross n identity matrix. With the rows corresponding to n minus b, which is b complement, set to 0. Okay, so basically kill these b complement once in the position of b complement and others you keep. That's your matrix P. And you can easily see that P square is P, right? Because identity square is identity, P square is also P, and 0 square is 0. So you have P square equal to P. So a more interesting thing is that the probability on the walk that every vertex Vi is in B in the walk, this is exactly equal to matrix product based on PA k times. A random walk is very tightly related to the matrix powers of A. But since here you don't want to go outside B, you always want to remain in B, so you should actually do matrix powering on P times A, okay, on this sub matrix. And so you will get a probability vector, and then you take the one norm, you sum the probabilities. So let's prove this. The proof is similar to what you have seen before for the general random walk. So the probability of V0 in B so for k equal to 0, this is just P1, right? And what is P1? P1 is just the size of B divided by n, right? So how many vertices there are, and you can be in each of them with probability 1 by n. So that's the probability of the union. So it is true for k equal to 0. Now probability of being in B after one step. So k equal to 1 case. So P1 bar is the probability vector at the 0th step, and after one step it will be, you only want to go from vertices in B. So probability of being in B after one step is this vector, probability vector P1 bar for the 0th step, and then you multiply by the submatrix, which is PA. Okay, and for this probability vector again take the one norm. So maybe I should write here that this matrix PA, P times A is the B cross B submatrix. So P square is P, and also when you multiply P with A or 2A, then you get the part of adjacency matrix A of interest, and that is what you multiply when you take a single step. Okay, and then generalize this to K. That's the full proof of claim 1. Right, so after k steps you get this expression PAK times P1, the vectors one norm. So notice that this PAK times P1 bar, you can also see this as, so what is PA square? So PA square you can see as PA times P1 bar, and which is also PAP dot 1 bar. Now how did I get this? I can repeat P because repeating P will still give you P. P square is P, right? So I repeated this single P, so I got PAP, and that is whole squared. Okay, so actually PA to the K times P1 bar is nothing but PAP to the K 1 bar. So you can think of this specialized to B or restricted to B random walk as matrix powering of P times A times P. Okay, and I should actually say here that PAP is this. So you multiply on the left and on the right, and then you have restricted your both rows and columns to B, and that is what will be relevant now. We'll be looking at powers of PAP. So hence now we'll study the spectral norm of this matrix, that is the factor by which it shrinks a vector. Okay, so what we will show next is this claim. So claim 2 now, for every vector PAP V bar is less than beta plus lambda times the length of V. Okay, so this matrix PAP shrinks every vector to something below beta plus lambda. Beta is the density of B amongst all the vertices, and lambda was the second largest eigenvalue of A. So why is this, right? This is a curious expression. How do you get this expression? So we will first club this part together, PV bar part. So we'll say that assume that V bar is supported on B. Which means that other coordinates in V bar are 0. If not, then you just replace V bar by PV bar. In the inequality. And notice that when you will replace V bar by PV bar, this RHS in the inequality will further cannot increase. Okay, it can only reduce, it cannot increase. So once you have shown that result, it will also imply this result, this inequality in blue. Right, so we can assume without loss of generality that V bar has only coordinates in B position, not outside it. So this cannot increase the RHS. And similarly, we can assume the coordinates to be non-negative. Because if there is any negative coordinate, then you can make it positive and prove the above result. Okay, so that will again not increase RHS. So you can assume coordinates to be non-negative, and you can also assume the one norm to be 1. Because if it is not 1, then you can just divide, you can normalize the vector V bar by it. Okay, so we have all these assumptions that we can make. With these assumptions, now let us write down. So remember that in this RHS you want beta and lambda to appear, right? So how will that happen? So you should beta you will get intuitively, you will get, because V bar's coordinates are only beta fraction many, and lambda, to get lambda somehow you have to relate LHS to the way A acts on 1 bar orthogonal, right? Because you know that the action of A on 1 bar orthogonal, the amount it shrinks, that is upper bounded by lambda. So you have to somehow relate with that. So what we will do is we will first write so PV bar is V bar because V bar is already supported on B, and write it as V bar in two components, 1 bar and Z bar. 1 bar direction and something orthogonal to it. Okay, so this is the orthogonal decomposition of V bar. So alpha and Z bar will be defined accordingly and uniquely. N1 bar V bar is equal to this all one vector inner product with V bar, which is sigma Vi, which is equal to 1, right? So N1 bar and V bar inner product is 1. So we get so now let us write it V bar as alpha 1 bar plus Z bar. Z bar is orthogonal to 1 bar, so that doesn't matter. So you get alpha times N1 bar 1 bar. N1 bar 1 bar is 1, right? This means alpha is 1. So by the assumptions on V bar, what we have deduced is that actually alpha will be 1. So V bar is 1 bar plus Z bar, where Z bar is orthogonal to 1 bar. So we have written V bar to be 1 bar plus Z bar, and this will be useful now to understand the action of PAP on V bar. So let's do that. PAP on V bar is PA V bar, which is equal to PA 1 bar plus PA Z bar, which is equal to A 1 bar is 1 bar, right? It's an eigenvector of A. So that's P 1 bar plus PA Z bar. So which means that, so you are interested in the norm of this, right? This vector. So the norm is certainly less than or equal to the sum of the norms. And this sum, when we will work it out, you will see that the first summand will give you promised beta and the second summand will give you the promised lambda. Okay, because Z bar is orthogonal to 1, so you can intuitively see why. And that is how you will get the expression of claim 2, which is beta plus lambda. So let's do that in detail. We bound these respectively by beta V bar and lambda V bar, proving the claim. So the first is P1 bar is less than equal to beta V bar. So this you deduce by, so P1 bar is you are only looking at B many, size of B many places and then summing up with weight 1 by n, right? So you will get beta n times 1 by n as 1 by n square and square root of that. So this is square root of beta by n. That's what P1 bar is exactly, right? The Euclidean norm. But how do I relate it to V bar, length of V bar? So that I have to calculate separately. So let's do that. If I look at this, the sum of the coordinates of Vi of V this is equal to the inner product of this elementary vector or this vector E bar B, where 1 is in the positions of B, otherwise it is 0. So 1 in B positions, that is EB bar. So sigma Vi is EB bar inner product with V bar. Now inner product is less than equal to product of the lengths. Okay, you also know that sigma Vi is 1, right? So you get that 1 is less than equal to EB bar is square root of beta n length, and V bar length we don't know, but now we have a lower bound, right? We know that V bar is at least 1 over square root beta n. So which means that P1 bar that we have calculated above, this is less than equal to beta times V bar, right? You can check this. P1 bar norm is square root of beta by n, and that's the same as saying V bar is at least 1 over square root beta n. Okay, so we have shown that P1 bar is small compared to V bar by a fraction of beta. Next thing we have to show is PA Z bars upper bound. So this we will show is smaller than lambda times V bar. Okay, so recall that Z bar is orthogonal to 1. So by the definition of lambda, or by the relationship of lambda with the action of A, you get that A Z bar's norm has to be less than equal to lambda times Z bar. The shrinkage will be more than lambda, right? That is what you can say. So which means that PA Z bar, this vector's length is smaller than that of A z bar, because P only restricts, right? So length at least is not larger than A z bar, which is less than equal to lambda z bar. So we have shown PA z bars at most lambda z bar, but now what is the relationship between z bar and V bar? So that is now just one step away. What you use here is that V bar is 1 bar plus Z bar. So which means that the norm of V bar square is, so use the sum of square property. So from this you know that Z bar is smaller than V bar. From which you know that PA Z bar is smaller than lambda V bar. Okay, and from both these small observations, what you have learnt is that PAP V bar is smaller than beta plus lambda V bar. Okay, this proves the claim. The claim 2 basically. So what next? So we have shown that probability of being stuck in these bad vertices is essentially dependent on this PAP to the K, and we have shown in claim 2 that PAP's behavior on a vector is shrinking it to beta plus lambda or smaller. Right. So now you can imagine how the subsequent proof will proceed. So since we now know that the spectral norm of PAP is smaller than beta plus lambda, so this is in fact strict inequality. Since the spectral norm is less than beta plus lambda, we can estimate the matrix product. To get the probability. So PA to the K times P1 bar 1 norm, it relates to the length of this vector as square root n times length. Right, this is the Euclidean norm, the length of the vector, which is equal to square root n times PAP to the K times 1 bar. That's an exact equality. And now from the above claim, you just repeat it K times. So every time you will get a shrinkage of beta plus lambda. And the length of 1 bar is n times 1 over n square root, right, which is 1 over square root n. So this is exactly equal to beta plus lambda to the K. So as we had claimed in this theorem, right, beta plus lambda to the K. So we have shown that probability of being stuck within the bad vertices is this much when you are doing a random walk. but we are actually interested in calculating the chance that half of your steps in the random walk or more than half are stuck in bad. Maybe not all, but more than half, right? So in fact, that also can be proved in a very similar way. So the above technique is strong enough to estimate the probability of being at B at specified steps. In the random walk. So for example, if you want, let's say you want 0th step and then second step and maybe 4th step. You want to be in B, then the probability is so then you can basically take the matrix product to be. So 1 bar is your initial vector, but 0th one you want to be in B, so you will multiply it with P. Then first step you don't care, so you will multiply by A, and then second step you do care, you want to be in B, so then you should multiply with PA. Okay, third step you don't care, so it's anything which is A. Fourth step you care, so it should be PA. So this is your matrix product. I am claiming that these kind of matrix products also can be analyzed in a way similar to the above. Okay, so this expression also can be analyzed, and the corollary that you get is for any subset of 0 to k. When you look at the probability over the walk that these vertices in I, Vi, they should be in B. Okay, so not all the vertices in the random walk, but the ones which are given in the set I, they being in B, this probability is also limited by power of beta plus lambda, and the power will be size of I. Right? So when I is everything 0 to k, then we showed beta plus lambda to the k. Otherwise, it is the number of vertices that you want in B. Okay, so you can also give a similar proof for this. So that I leave as an exercise. And hence, this now you can use. This is a very strong result. You can now use it to estimate the chance that more than half of the vertices in the random walk are bad. So let's complete the application. So say your algorithm M uses R random bits and has error less than equal to beta. So in the space of 0 1 to the r, beta fraction are bad. So define this B to be subset of 0 1 to the r be the bad strings and you know that the size of B is less than equal to beta to the n. N is 2 to the r. Okay, so in the whole space of r bit strings, beta of them are bad, that is the set B. So what kind of an expander should you employ here, looking at the probability estimate? So employ an n comma d comma lambda expander G to walk where this beta plus lambda should be small enough so that the probability estimate works out. Okay, so we are thinking of the vertices as 0 1 to the r strings and B are the bad vertices. So when you are doing a random walk, you want to hit these vertices at most half or smaller than half the time. So let V0, V1 to Vk be the walk. Now the majority vote when you run this algorithm M on VIs, this majority vote is wrong if and only if at least half of these VIs were bad. So size of I is at least half. Right, that's the only case when the majority vote fails. Otherwise, the majority vote would have been correct if bad vertices were few. So the probability of this happening in the random walk, so probability of this event, right, that there is an I k plus 1 by 2 size such that for all I you are stuck in Vi, this probability is less than, so possibilities of I is it doesn't exceed obviously number of subsets, which is 2 raised to k, and once you have fixed I, you use this theorem that we just proved, that is b plus lambda to the k minus 1 by 2. Right, so k plus 1 by 2 is the size of I. minus 1. So you get k minus 1 by 2. That is the error probability, that you use the expander, explicit expander, run mx, take the majority vote, and still you get a wrong answer. So that probability is limited by this expression. So you just have to take beta plus lambda. So assuming beta plus lambda to be, let's say, less than equal to 1 by 8, okay, which you can ensure. You can assume that, you can easily assume that the algorithm beta was, the error in the algorithm was, let's say, less than 1 by 16, and lambda also is less than 1 by 16 for the expander graph. So you will get this expression, you will get this bound beta plus lambda at most 1/8, and that will give you error we get error probability less than 2 raised to minus k by 2 for random bits. Random bits that you need is r plus k log d. Okay, so for roughly r plus k random bits, you are getting an error of 2 raised to minus k by 2, assuming that you have a good enough expander. That is what we have shown. Right, so this finishes some major properties of expansion and how it can be used in general. Right, for general algorithms, you can use expanders and very large expanders, as long as they have constant degree and they are very explicit. So for every vertex, the neighbor can be found easily. So now, how reasonable is it to expect these explicit expanders to exist? Right? How can we construct them? How can we find them? So this is what we will focus on next. So we'll now construct explicit. The new topic that we begin is, it is still within expanders, but now we will want explicit expanders, constant degree, very large, but very few neighbors and easy to find. So explicit expander constructions. So the nice thing about the methods in this topic, in this chapter, will be that ultimately you can start with any graph, undirected graph, and once you do these operations in a certain sequence, it will become an expander. Okay, so it is not only a construction to get big explicit expanders, but also to convert any graph into an expander. So it will have multiple applications. Okay, so you can do what we just saw before, this success probability boosting, minimizing the number of random bits, but you can also solve connectivity in log space. So we will see that application later. So we will construct an explicit expander family. Okay, so remember that when we construct expander, we mean infinitely many expanders, right? It should be constructible for any size. It shouldn't be that you construct only one graph. That would have little to no utility. So you actually have to, somebody gives you a parameter, let's say the size of the graph, and then you have to construct an expander bigger than that. So it's an infinite family construction. And there are three main operations, algorithmic operations, which will be used. So idea is to use three kinds of graph products. So these operations, we will call them products because in some sense they will be multiplying two graphs. Okay, but the definition of multiplication will be different. So it may be powering a graph or just matrix multiplication for the adjacency matrix. Second type will be tensor product, and third type will be a combination of both, which is called zigzag product. And there will be a trade-off between degree and spectral gap. So trade-off means that in these operations, if you make the degree large, if you want the spectral gap large, you can achieve it by increasing the degree. But then you cannot afford too big a degree because you want degree to be constant. Okay. And you also want spectral gap to be constant. Both of them, you want them to be constants. So we have to keep a balance so that both of them remain constants, and spectral gap increases as much as possible, and degree is minimized as much as possible. So we'll need a new representation of graphs. So you already know two graph representations. One is the vertex edge drawing, or the actual diagram of the graph. Second is thinking of it as a 0-1 matrix, which is adjacency matrix, or normalized adjacency matrix, which is a stochastic matrix. And third is via something called rotation map. So you can think of it as follows: vertex u and vertex v, these are two vertices. Now they are neighbors of each other, so you can think of v as a neighbor of u and v as a neighbor of u as a neighbor of v. Okay, there is a single red edge, undirected edge, which makes them neighbors of each other because it's an undirected graph. So when you think from the point of view of u, v is let's say it's the ith neighbor of u, and when you think from the point of view of v, u is the jth neighbor. Okay, so basically we want to store for every vertex u, we want to store the neighbors in a certain order, and since you will do this for all the vertices, so u comma I will take you to v, and then v comma j will take you to u. That's the representation. So if G is an n vertex, d degree, connected graph, Yeah, so we'll look at connected graphs only, and then connected graphs, our operations will ultimately make it an expander. That's the plan. So let's let G be a connected graph, n vertices d degree. Then we label each neighbor of each vertex using 1 to d numbers. Each vertex has d neighbors, number them 1 to d, and then define a rotation map. We call this map rotation map. G hat, it's n cross d, so it will send this the way it will send is, let me define it here then. So it will send v comma I to u comma j. Okay, so you should read it as v is the ith neighbor of u. So u is the ith and v is the jth. Yeah, so you should read it as the ith neighbor of v is u. Okay, moreover the jth neighbor of u is v. Okay, so this is the natural information associated with an edge. Okay, all the four things will be related like this, and we'll think of v comma I to u comma j as a map, n cross d on the domain n cross d. So where u is the ith vertex of v, and v jth vertex of u. Now note that G hat is a permutation on n cross d. So why is that? Why is it a permutation? It's a permutation simply because the image of u comma I is exactly one pair, and if you look at the pre-image of so v comma I's image is unique, and the pre-image of u comma j is also unique. Okay, simply because of this picture. If you look at this diagram, from this it is obvious. So that's why it is a 1-to-1 onto map. Is 1-to-1 and onto. So for on, I mean it is every pair is covered. It's onto because of connectivity, I guess. Do you need connectivity here? Yes, I think you need connectivity, some weak form of connectivity. So because of that, it's both 1-to-1 and onto. So the three products that we will consider, so given G and G prime in the above representation, we'll define 3 kinds of products. So the first will be matrix product or path product. Okay, second will be tensor product. And third one will be replacement product. And related to the replacement product, we'll also have a zigzag product. So actually 4 products. Okay, so we'll define these things next time, and then we'll use these 4 products to improve expansion. Combining them, we'll improve expansion. Okay, they will have different strengths and weaknesses, and in combination they will work very well.